Welcome back to the Health Longevity Secrets Show with your host, Dr. Robert Lufkin. His book, titled Lies I Taught in Medical School, is a New York Times bestseller. See the show notes for a link to download a free chapter. And now, please enjoy this week's episode as we look at the possibilities of mitochondrial transplantation with Tom Benson.
What if we could reset our cellular batteries? In this fascinating deep dive into cutting-edge longevity research, Tom Benson reveals how mitochondrial transplantation could revolutionize how we treat age-related diseases and potentially add decades of healthy living to our lives. The conversation begins by exploring the extraordinary nature of mitochondria, those tiny power plants within our cells that generate 90% of our body's energy through molecular rotors functioning like miniature jet engines. With approximately a quadrillion mitochondria comprising up to 10% of our body weight, these ancient organelles trace back to a symbiotic merger with cellular ancestors over 1 billion years ago. Unlike the nuclear DNA we inherit from both parents, our mitochondrial DNA comes almost exclusively from our mothers, creating fascinating maternal lineage patterns where thousands of family members share identical mitochondrial DNA. As we age, this mitochondrial DNA gradually accumulates damage with factors like stress, smoking, and medical treatments accelerating deterioration. By the time we reach our 90s, this decline reaches a critical threshold that appears to drive much of the aging process. The most exciting revelation comes in learning that mitochondria naturally move between cells in our body, and scientists are now leveraging this phenomenon through transplantation techniques. By harvesting mitochondria from stem cells grown in bioreactors and re-injecting them, researchers are seeing remarkable improvements in cognition, strength, and immune function in aged mice, essentially restoring youthful cellular energy levels. Now, human trials are already underway, although still at a very small scale. For anyone fascinated by the frontiers of longevity science and the quest not to just add years to life, but life to those years, this conversation offers a glimpse into one of the most promising approaches emerging today. This episode is brought to you by L-Nutra, maker of the Prolong fasting mimicking diet. If you'd like to try it, use the link in the show notes for 20% off. What if your routine CT calcium scan could tell you even more? Now from a single scan, you get 4 powerful reports, not just your coronary artery calcium score, but also your arterial age, liver fat levels, and bone mineral density, with no added radiation or time. It's early detection made smarter, spotting heart disease, metabolic dysfunction, and bone loss before symptoms begin. And now it's available anywhere in the US, no prescription needed. 1 scan, 4 reports, life-saving insight. Use the code LUFKIN20 for 20% off.
And now, please enjoy this week's episode.
Hey, Tom, welcome to the program.
Hey, Rob, nice to see you. Glad to be here.
Well, likewise, I am so excited about this topic today, mitochondria, but not just mitochondria, but mitochondrial transplantation.
Yes,
This
yes,
is
yes.
so cool. But before we do that, let's just take a moment. This is the first time you've been on the show. Can you take a moment and just tell us a little bit about your background and how you came to be involved in this space?
How did I get into this crazy idea? Well, I have been starting, high-tech businesses for maybe 40 years now. I am kind of a Silicon Valley person. I started a software company way back when, and actually, I was one of those people. I was in Stanford in the physics master's in physics, and decided to quit and start a software company because that was the hot thing back then, right? And then I did that for a while, and then got moved back into science and did some different startups, and including a fusion startup back before fusion was hot. And then I ended up working at Stanford Linear Accelerator, which is the big 2-mile long giant linear accelerator up above Stanford. And we were imaging mitochondria as part of our our work that we were doing, taking these tiny little photographs of mitochondria, and I just got really interested in the field. So that's I started reading about it, and I I saw that there was all this like amazing new research that was popping up that nobody was talking about, that was just completely changing our understanding of mitochondria, and I just felt like I should do something with it. So
Uh, and you
yeah,
guys were taking pictures of mitochondria with the accelerator, or
yeah.
is that
Well,
what it
no,
was?
it was actually it was a I always tell people I worked at a giant underground laser beam. It really what it was. It was it's called the LCLS. It's a light source, what they call an X-ray light source, and you do X-ray crystallography, which is how you take pictures of tiny little molecules. So they were looking at mitochondria and chlorophyll and all these interesting molecules, and I just saw some interesting stuff that I didn't ever realize was true about mitochondria. So
and we're and we're about to find out some of those. It's
about
like
to find out exactly.
I I'm embarrassed to say, as long as this podcast is going on, we haven't had that many episodes focused on mitochondria, and that is despite the more information comes out, the more we know how fundamental they are to metabolic health and so many of the chronic diseases that
Right.
we talk about on the show and that we're all facing. It's the 21st century epidemic of biblical proportions. So
Biblical, yeah, just about. Yep.
so let's go back to ground zero 101. What what are mitochondria and why are they important?
Yeah. Well, yeah, and I agree with you. I think that the thing that attracted me to this work was that it looked to me like there was this whole area of medicine that was just a blind spot. And I really believe this. We just have not been focused on mitochondria at all in medicine. We've been looking at the nuclear DNA, the nuclear genetics, which are very important. And there's this whole range of diseases that appear to be mitochondrially driven. So the mitochondria are tiny little, what they call organelles, but they're like these little, almost like tiny little bacteria that are inside the cells. And a typical cell might have 100 or 500 of them. They're really, really, really small, and they float around. And they're where the cell generates all of its energy. Okay, so 95% of the energy in your body comes from these little mitochondria. They literally are, they call them the power plants of the cell. That's what you saw in your high school textbook, right? And they literally are power plants. They have tiny little spinning molecular rotors on them, almost like I tell my kids, I said, you are powered by tiny little jet turbines. Okay. Every mitochondria has about 7,000 of these tiny little jet turbines that are spinning away, and they're combusting glucose and oxygen and creating hot gas and using that to spin a rotor. It's just like a power plant in that we have in our world, except a zillion times smaller. And you have about a quadrillion mitochondria in your body. We are 10% by body weight composed of mitochondria, generally. So it's a lot, okay? And they merged with they merged with our DNA about 1 billion years ago. There was a mitochondrial ancestor and some DNA, and they came together and created this new type of cell. It's the basis of all life on Earth today, really, is mitochondrially powered cells. Okay. So whatever they're doing, they've been perfecting it for 1 billion years. So it's pretty well perfected.
So,
And
so these, let me just interrupt you for a second. Just that point is such a fascinating thing. So the understanding, the accepted understanding is that a primitive organism was a mitochondria. It existed by itself, and then merged with another cell to make these modern cells.
correct, correct. And so,
In somewhere in the distant past,
right,
and
right.
but they actually were for, and now they're part of us in sort of an ultimate symbiotic relationship today.
Exactly. And over hundreds of millions of years, they've been optimizing that relationship. So the mitochondria used to be much more self-sufficient. And of course, it's given away, like a lot of its stuff has been put into the nuclear DNA now. Each mitochondria has its own tiny little ring of DNA, which is completely different from our regular DNA. So, I mean, we have our nuclear DNA, which is the, chromosomes that are, the mother and the father, the chromosomes come together. That's our regular DNA. It's about 8 billion base pairs, I think. The mitochondrial DNA is a tiny little ring and it's only 16.5 kilobits. So if you think of a motherboard on a computer, it's the equivalent of that teeny weeny little chip over there that just like manages the battery or something. It's really, really small. Okay. But if they get screwed up, the power plant stops working. They're absolutely critical to the operation of the power plant. Okay. These little mitochondrial DNA.
And the DNA, just to emphasize that, again, what you said was our main cell in the nucleus. We get DNA from our mom and dad, and it's a mixture. Each child is a mixture of the parents, and that's really important. The mitochondrial DNA, though, we just get largely almost 100% from the mother, right?
Yeah, basically 99.99% comes straight from the mother, came straight from grandmother, great grandmother, great great grandmother. So, and it gets passed down via all the maternal channels. And so, if you have a big family, there could be thousands of people in your family who all have exactly the same mitochondrial DNA as you do. So it's not an individual DNA; it's a family DNA. It's very interesting. Okay.
Yeah.
And in fact, it's also regional. There's like, groups of mitochondrial DNA have migrated throughout the world from Africa 200,000 years ago. And if you go to Nordic or Eskimo mitochondrial are slightly different from tropical mitochondria, for example. They're modified in little ways, but they're all completely interchangeable. And so whatever you get when you're born is what you get.
And so this maternal transmission of mitochondrial DNA has to do with the fact that sperm largely don't carry mitochondria from the male. And so it's just in the egg from the female. But as you say, it creates some fascinating genetics and family tree things that, a few years ago, there was the mitochondrial mother hypothesis that, people were talking about.
That's right. Mitochondrial
fascinating.
Mitochondrial
Yeah.
Eve, right.
Yeah. And tracking back mutations back to a common mitochondrial mother origin.
Right. And the thing that's been interesting in the last few years, I said there's been all this new research. What we found out is that it used to be that a lot of people thought, oh, well, whenever the cells need new mitochondria, just makes them. And so we don't really have to think about that. But what we're finding out is that mitochondrial DNA, you get a giant hunk of it from your mother. Every egg cell has 500,000 copies of the mitochondrial DNA, but they're really tiny. So it's like you really actually, in a typical egg, you have two completely separate sets of DNA, and we never talk about that one. It's just as much, and we don't talk about it. But it turns out that there are enormous implications for health, for chronic disease, and also for lifespan. So what we have found, and this is, by the way, everything I'm saying, I just want to do I'm going to do the disclaimer here. Everything I'm saying is very, very new. A lot of it is unproven. These are my theories and our company's theories, but don't, this has not been tested in human beings, so don't take this as being fact. Okay, this is very new. But anyway, what we're finding is that as people age, their mitochondria, as the years go by, your mitochondrial DNA starts to kind of fray. It gets broken up and damaged, and it's steady. And when you reach a certain point, if you make it to say 90, 95 years old, you reach a certain point where it seems to really fall off a cliff. And so we believe that is at least 50% of what's driving aging in our bodies is that decline of that mitochondrial DNA. Okay.
So the mitochondrial DNA ages, not unlike there's other aging factors and genetic mutations may or may not be the primary driver of regular DNA aging, but it certainly it's foundational, and I mean
Right.
it is. And so, but we know about like telomeres. Are there telomeres in mitochondrial DNA?
No, no, because it's a ring. It doesn't need
Yeah,
telomeres. Telomeres are
yeah,
only for the ends, right? And in
right.
fact, there's a lot of data that implies that telomeres may be, in fact, a type of clock that the cell is using to track the decline of the mitochondrial DNA in order so that the nuclear DNA and the mitochondrial DNA can kind of keep balanced as to where they think they are in put in your lifespan. Okay, so the nuclear DNA is making changes to our bodies as we age in order to allow for the fact that it knows that there's going to be this reduction in energy production by the mitochondria. And that's very, very new conceptually, but that's what we think is that the telomeres, and also there's this thing called epigenetic reprogramming, which is the epigenome on the nuclear DNA. It gets modified as you get older, and we think a lot of those modifications are helping us kind of manage this mitochondrial decline.
Well, so before we get into epigenetic reprogramming,
Yes.
before we leave telomeres, is there a Hayflick limit for mitochondrial DNA or
No, it's a complete, see, mitochondrial DNA are bacterial DNA. They're a completely different system. They don't have sexes. There's no male and female. It's what's called clonal inheritance. That's why there's no contribution from the father. There's no changes over the years. It just clones itself over and over and over again for a billion years now. Um, but what happens is as you age, if you get this, let's say when you're a baby, your mother has basically given you an ideal inventory of mitochondrial DNA. You start with a whole bunch of them and they're really perfect. And then as you get older and older and older, they just degenerate and what you call replication errors. Every time the mitochondrial DNA is reproduced, which it happens constantly, there's always the odds of some little bit of noise getting in there just by accident. Okay. And if you're under a lot of stress, a lot more noise gets in there because it replicates very quickly and it's very messy. It doesn't do a very good job. That's why we found that things like stress and smoking, they tend to cause a lot more mitochondrial damage. And so by the time you're 75, you've already burned them out. Okay.
so the same factors, if I understand you correctly, then the same drivers of mutations that damage our main DNA also damage our mitochondrial DNA. Although it's a
Correct.
different type of DNA, it's still
Correct.
susceptible to smoking, stress, reactive oxygen species, all these kinds of things,
All that
correct?
stuff. Right. And you also can be born with prematurely aged mitochondria. There are children that are born, there are tens of thousands of children in the world who were born with prematurely aged, broken mitochondria. And they've often, it's really a horrible thing. I mean, there's no cure for it. And they just die by the time before they even are babies. They just die within a couple of years. Sometimes they make it into to be teenagers, but their bodies never work properly. They go blind, they lose their hearing, they can't move because they only have 20% healthy mitochondria out of all of their mitochondria. They might only have 20%. Okay. And so mitochondrial dysfunction can actually hit you at different ages. But
Yeah.
it's pretty much automatic as we age. That's the natural way of your mitochondria going downhill is just from being around long enough. If you're 90 years old, you've had time to get a lot of errors in the mitochondrial code. Okay.
Yeah, when I just emphasizing what you were saying, when I went to medical school, which was a long time ago, we studied, we learned about mitochondrial disease, but it was a short list of devastating congenital abnormalities that the children, sadly did not do well, and they
No
did
cure at
not
all.
survive long.
No
But
cure. Yeah.
now, but it's interesting that today that there's increasing evidence that mitochondrial dysfunction is at the root of all these chronic diseases that everybody gets.
Right. And
That
so,
practically all of us are going to die of one of these chronic diseases, and mitochondria appear to be at the root cause of that also.
right. And by the way, you can there are some cases where we suspect that you can acquire mitochondrial damage. For example, if you take fluoroquinolone, which is known as Cipro, which is an antibiotic, if you take too much Cipro damages mitochondrial DNA. That's what it does. That's what it's designed to do, because the bacteria that it's attacking all have that same little ring of DNA. See, so you're killing off the bacteria, but you're also killing off the mitochondria in your body. And there are people who have gotten overdoses of that where they have acquired mitochondrial mutation disease when they're in their 20s and 30s, and they have the same symptoms.
Well, before we get into that, let me back up one last thing
Yeah.
and emphasize
Yeah.
that. So we talked about our main DNA and aging. We talked about mitochondrial DNA and aging, and mutations occur in both of them. Recently, there's a revolution in our knowledge about, like you mentioned, the epigenome, the
Yeah.
way
Right.
expression is controlled of our main DNA, our nuclear
Right.
DNA.
Right.
Is there a similar, what is the analog of the epigenome for mitochondrial DNA? And
Well, what we just discussed is the analog, and the epigenome is adjusting the nuclear DNA. It's adjusting the gene expression to allow for the fact that it kind of evolution knows you're getting older. And so it changes the genes so that instead of being a 25-year-old, you're now a 70-year-old. And that means you're reducing skeletal muscle and you're letting the skin go slack. And there's all these things that the body does. I think it's pre-programmed to do it to allow us to live longer with what we have. If you look at an antelope, for example, that's 150 pounds versus a human that's 150 pounds, the antelope will live maybe 30 years. That's its max lifespan. We live to be 90. So why do we live 3 times longer? That's a really fundamental question. I think it's because nature has programmed us to use our resources slowly, to ration the resources so that we live to be older, because for our particular species, being older is better because then we can pass knowledge on to the young people. And there's all these evolutionary theories why we have such long lives, okay? But that's all something that's done at the nuclear level, allowing for the fact that the mitochondria will burn out. If they'll burn out in 30 years, they'll burn out in 90 years. It depends on how they're used. Okay. And so that's the new theory behind mitochondrial aging. And the implication would be, and this is part of the longevity field. I mean, of course, there's now all these people throwing, resources into developing longevity tools. There's a whole bunch of companies in Silicon Valley, for example, that have been pouring funds into epigenetic reprogramming, which is where you go in and you reset the nuclear DNA and convince it that it's 40 years younger. Okay, you just basically reset the programming. But what we say is, well, the other half of the issue there is you've got the mitochondrial DNA, which is also old. You got to reset that too, or they're going to be out of balance, and that will be bad. That would be a very unhealthy. Okay. So that's what we're working on. That's our half of the new, this new idea of age, of health span extension is what they call it.
let me summarize that if I can, just and then you can go on. This is so important.
I know this is deep. This is
I,
complicated stuff, so it takes a while
I
for.
want to make sure everybody follows it because this is so good. It's so important. So the epigenome in the central in the nuclear DNA, it's histones and methylation and everything. Is it
Right.
a similar mechanism for the mitochondrial epigenome that controls expression? Is it
No,
similar?
it's a completely different mechanism. We're trying to do the same thing, but they're just completely different. The
So
mitochondria and the nuclear DNA are like whole different worlds. Okay. So,
So the tools that are so effective in reprogramming nuclear DNA, Yamanaka factors, and other epigenetic reprogramming techniques. So the mitochondrial DNA doesn't respond to the usual partial epigenetic reprogramming, Yamanaka factors, and
not the
other
same way, not
things,
at all, right? Because
except through except through nuclear effects. But
yeah,
specifically on the mitochondrial DNA, it doesn't reprogram it, right?
yeah, because there is no real reprogramming. There's no epigenome. There's not a real, it's not the same as the nuclear DNA. The nuclear DNA is very, very well protected and very, very well has tremendous quality control. And so it stays pretty pristine. And then the epigenome is what changes it over time. The mitochondrial DNA is just a completely different thing. Think of a giant factory with smoke and flames billowing everywhere. Those mitochondrial DNA are just getting burned up. It's a factory, okay? And so you don't have the frou-frou niceties of the nuclear DNA. It's really um, so it's a completely different approach to fixing it, but it's the same idea. We need to fix both at the same time, okay, in order to extend health span, in order to reverse age, for example.
So before we get into how to fix it, a couple other just clarifications kind of to set the framework. You mentioned that certain things burn out mitochondria at a faster rate or exhaust them. What kinds of things are those?
Uh, it's the things that we all know, right? And now we're seeing all these papers are coming out. There was a whole series of papers, brilliant papers from Columbia, from some researchers there that showed how stress hormones in the bloodstream cause the mitochondria to replicate more quickly, but they're replicating sloppily, and so then the mitochondrial DNA very quickly it gets completely trashed. Okay. So stress. Well, what a surprise, right? Smoking, of course. Smoking is enormously damaging because it's hitting all the mitochondria in your lungs and it's damaging them
Is that
with
from the
smoke.
tobacco or from the combustion products, or do we know? Because I like,
No idea.
okay.
No idea. So stress, tobacco, drinking, alcohol, of course, anything that is any kind of disease. Like let's say you get cancer and you go through chemotherapy. Well, we're doing that. We have a thing called Mito clock that we created where we can actually look at the number of these damaged sectors in the mitochondria. It's almost like a hard disk. You can count the number of damaged sectors. And so we go in and we analyze the mitochondrial DNA in some mitochondria that we get from urine. We could do a urine sample. And you can see it's this decline as people age. And our feeling is that when you hit something like chemotherapy, it's going to go boop, it's going to drop 10%, boom, right there, because chemotherapy is specifically designed to destroy mitochondria. Okay. Bone marrow transplants, tremendously damaging to mitochondria. Cipro, I already talked about that. Maybe some viral infections. There's a series of papers that have come out that have shown that COVID specifically damages mitochondria.
So now we know some of the things that can damage the mitochondria,
Right,
and we know that
right.
aging is associated with decreased mitochondrial function, increased damage. What are some of the symptoms of mitochondrial damage? Putting aside those childhood diseases, but just like when should we suspect mitochondria? Are there any specific symptoms, or is it more a generalized
Yeah,
thing?
I mean, Parkinson's, Alzheimer's, ALS, AMD, which is macular degeneration, sarcopenia, which is muscle weakness. Basically, all age-related diseases. Every time somebody says, "Oh, is mitochondria involved in this age-related disease?" and the answer is always yes, because as the mitochondria decline, what happens is all these diseases kind of pop up. All right. Arthritis. Or I'll give you an even simpler example. When people who are in their 80s get, let's say, pneumonia or COVID, they end up in the hospital, right? And we all know this. I mean, who ends up in the hospital with COVID? The old people. Well, why? Well, the doctors say, well, because their immune system isn't strong enough to fight it off. Well, why is their immune system not strong anymore? Let's just ask the dumb question. Why? Well, because they're old. Well, what does that mean? I mean, you could keep asking this question. At the end of the day, what we found is the mitochondria in their immune system cells, in their white blood cells, are very weak. They're equivalent of a battery that's been discharged 75%. The little rechargeable cars that you drive around, or the rechargeable drills that you use at your house. Maybe you've used up half the battery, and so it just doesn't go as fast as it used to. So that's all these white blood cells. They don't have very strong mitochondria, and so they can't fight back. And so you can't fight off an infection. We've done experiments in mice where we've taken a whole bunch of young mitochondria from young mice. We just get it from their platelets in their blood. And we inject them into old mice who've gotten this. We give them a disease and give them these mitochondria, and they just brush off the disease as if they were 30 years younger, or the equivalent of 30 human years younger. Okay. So we can re-energize the immune system. We've been doing that for years. And what if we could just do that with all the old people in all the hospitals? I mean, just think
Yeah.
what a change that would be. And it's not even that complicated to do it.
Yeah, yeah. So we sort of set the stage here, mitochondria, how important they are in aging,
Right.
how how they affect so many diseases. Now, you founded a company that is working with the an idea that may be a solution for this. So
Right.
tell us about mitochondrial transplantation. What is that? How
Transplantation.
does it
Right.
work? Go for
Starts
it.
definitely starts sounding like science fiction once we're getting to this point. But I'm telling you, everything I'm about to tell you is happening. It's real. So yes, we're doing what's called bioreactor grown mitochondrial transplantation. Okay. And when I said there was a whole bunch of new research coming out that I got excited about, what we found about 10 years ago, some researchers tried transplanting mitochondria from one part of the body to another. And everybody said, oh, you're crazy. That'll never work. Well, it worked fine. It turns out that mitochondria don't just sit there in the cells. What we're finding out is that mitochondria are constantly moving around between cells. They just go right through the walls of the cell. There's a little mechanism that lets them through. They are transported in the blood constantly. They're transported between different types of brain cells. So, for example, the astrocytes in the brain, which are a type of brain cell, it seems to be that's where they're kind of manufactured. And then they're put into little tiny vesicles and they float over to the neurons, and the neurons use them to run. And then when they get burned out, they send them back. So it's kind of like a little manufacturing site for the neurons. Your platelets in your bloodstream, uh, you have about 1 trillion platelets in your blood at any given time. Every platelet has 5 mitochondria in it on average. And whenever they reach the end of their lifespan, they squirt those mitochondria out in these little what we call extracellular vesicles, and they're absorbed by the rest of your body. And so the platelets are trans, uh, transplantation. So it's an internal bodily transplantation of mitochondria that's happening constantly all the time. So your body, there's been 1 billion mitochondria that have been transplanted through your bloodstream in the time that we've been talking.
And one question I forgot to ask: how do mitochondria reproduce, or do we just get one set that stays with us? And
No, the cell reproduces them. So when the cells need more of them, they divide them, just like, it's called mitochondrial biogenesis. The cell can do it. The mitochondria can't divide by themselves. They don't have all the equipment anymore because they've handed off all the replication equipment to the nuclear DNA. Okay.
uh-huh, uh-huh.
So you start as an egg with 500,000 copies of the mitochondria DNA, and by the time you're an adult, you have about a quadrillion, 10 quadrillion, whatever the number is, mitochondrial DNA. And then over the years, those are constantly being rebuilt and rebuilt and refreshed.
So,
Okay.
so within our body, then the mitochondria move all over, and they do internal transplantation, sort of
That's it.
all the time. But that's not what you're talking about. You're talking about something completely
Well,
different. What is that?
we're taking advantage of that whole process where we say, okay, if the body's already doing this, maybe we could just supplement it. Okay. If you've already got a flow of mitochondria in your blood, as you age, by the way, that internal amount goes down, just what you'd expect. Okay. So what we're saying is, well, gee, if we could supplement that and prevent that reduction in that internal flow by giving you an external source of mitochondria, maybe we could keep you healthier longer. And so what we do is we take your stem cells, we put them in an external bioreactor, which is pretty common these days. A lot of people who do this for other sorts of gene therapies. We grow those cells in vast, vast quantities. We extract the mitochondria, and then we inject them back into your body. And the idea is to basically, if your mitochondria are declining 1% per year, until you're 90, we're going to try to boost you back up again and get you back to the where you have maybe 10 or 20% more than you had before.
And so the idea of using my stem cells for my mitochondria, it eliminates any transplantation rejection or
Right,
immune system
right.
factors and all. And let's come back to that and hold that thought in a minute. Are there any possibilities for, because of the simplified DNA in mitochondria, for using, say, not my own stem cells, but from a female family member or something like that? What
It's
are
possible.
the challenges, or is that?
And by the way, let me just say one thing. This is not just us. There's a whole movement now around the world pushing this concept. There's several companies and several startups in different countries, Israel and Switzerland and other places. We just had the first annual mitochondrial transplantation conference about a month ago in New York. In
Congratulations.
New York, yes, and some amazing people at Northwell Health, which is a hospital out there, did this. There's universities all over the country now are studying this and finding out, oh, we can help people who've had heart attacks and strokes and wound healing. They're finding all these uses for it. And so it's growing very, very quickly. Our focus, and of course, these kids, as we talked about, who have this disease, there's actually human trials going on right now to try to help these kids by giving them healthy mitochondria. We're taking all of that and trying to apply it to old people. That's what Matrix is focused on.
Because the kids obviously wouldn't be able to use their stem cells because their stem cell mitochondria would be dysfunctional,
Right.
presumably.
So in that
So,
case, we
yeah.
might go to a sister who doesn't have the disease, but has exactly the same mitochondria, and we might use those mitochondria for these transplants. And since
Mhm.
they're identical, there's no reason that it shouldn't work just fine. Um,
And of all these at this conference of all these different companies, they're all looking at different spaces and different
right,
kind of
right,
applications and approaches.
right, right.
So your company is looking at the longevity application of it for essentially not just living longer, but these chronic diseases that determine our longevity, really, for
Right,
all
exactly.
of us that
Exactly. Yes.
that do that. What are the challenges you're facing now? Like, where are we on this path? Shall I schedule my transplant now or book
Well,
some time?
it's funny because I tell people we've been around for 4 years and we're a tiny company. I mean, we've been getting just angel investments from people who want this to happen, and it's always nice when it happens. Um, we're at the point where I'll joke with people, I've got a big red start button on my table, and as soon as we have enough funding, we need to get enough funding. I'm going to push that start button, and we're going to do our first full human trials. We're ready to do that immediately. Okay. So it's the biggest challenge is funding. It's just so new, and
Yeah.
new things. the government, actually, some of the government groups are very interested in this, but it just takes time for people to, get there. So,
And what have there been any like really exciting home runs or lab work or anything at this conference or that you're aware
yeah.
in this space that we can point to and say, see, it does work,
Oh,
or
yeah,
yeah, like
absolutely. Absolutely.
what would you like to highlight from that?
Well, okay. So there's two things going on. First of all, we've been doing a lot of injections into mice, and we've now gotten to the point where we've transplanted up to 1% of the total mitochondria in the mouse per injection. So we give that mouse one injection, and as I just said, you're 10% mitochondria. So you can imagine how much that is. It's a huge amount. And well, oh, well, will it kill the mouse? That was our first question. No, the next day, and these are in really old mice. These are 27-month-old mice, and that's about the equivalent of about 90 years old by human years. The next day, the mice are running around like crazy. They're so energetic. It's like, wow. It's like it really, I think it gives them kind of a buzz because they get all this, it's pretty quick how quickly it affects them. So after doing that over the course of 10 weeks, what we're seeing is significant increases in cognition. We do all these maze tests, and they're much, much faster doing the maze tests. We're seeing significant increases in strength and endurance. So they run on their wheels, they can hang on to things. They have what's called grip strength. And then very significant increases in immune strength, where they just kind of shrug off infections like they were young again. So, and in the longevity world, those are the three things that you kind of use as your starting point: cognition, muscle, and immune strength. Okay, if you can get those, you're doing really well.
Yeah, I mean, I'm sure some of our listeners are probably thinking about, many of them are interested in longevity, like we're talking about, and they've been hearing about stem cells, like you mentioned, and regenerative medicine, and they go, well, hey, I'm already going, offshore to get my stem cells.
Yeah, yeah, right,
Will
right.
this accomplish the same thing, or how is it different? If I get my stem cells and I don't grow them in a bioreactor for mitochondria or anything like that, but just my own stem cells, will I get the benefit of young mitochondria with that, or what
Well,
happens there?
yeah, a lot of people they go to Panama or they go to they go Los Cabos or wherever, and you can get those kinds of treatments. What I always tell people is that mitochondria are, I mean, we are in fact a type of stem cell treatment. It's just that we're taking the stem cells and we're squeezing out kind of the magical ingredient in the stem cell. And the reason is that when I say I'm giving you 1% of your mitochondria per injection, that's 1,000 times larger dose than a typical stem cell treatment. Okay, so at the end of one of our full treatments, we will have given you as much as 10,000 stem cell treatments.
Mm,
It's
mm.
just what I will say is there's nothing wrong with stem cells. They work fine, but they're just not enough. You need big amounts. When you're 90 years old, I mean, you've lost so much by the time you're 90. We've got to pump you full of new materials, and the mitochondria are kind of the rocket fuel component. So that's what we focus on. Okay. Um, a lot of our volunteers for our trials are already getting stem cell treatments, and they get a little benefit from it, but it doesn't last very long. So,
And so again, further comparison with stem cells, we hear about side effects with stem cells. They're
yeah,
not without risks,
yeah,
for
yeah,
cancer and other things.
right.
Are those risks the same with mitochondria? Are there additional risks or are they diminished? How does that risk profile look with
Our best
mitochondrial
guess is
transplant, do
that
you
they're
think?
significantly less risky. And that's another reason that's why a lot of people are jumping onto mitochondria because it seems to be a lot less riskier than the stem cells. And the reason is that when you inject stem cells, I mean, stem cells are huge and they have their nuclear DNA in there. And if something goes wrong, that nuclear DNA can get damaged, and then you're putting damaged DNA into your body, and that can cause cancers to grow, teratomas, right? Whereas if you do mitochondria, there is no DNA in the mitochondria except for the little ones, which don't have any they don't have the ability to cause any kind of cancers. And so the mitochondria, you're getting all the benefit without as much of the danger. That's what we've seen so far. Okay. I also do want to say there have been human trials on this. Human trials have been happening for the last couple of years, but they've just been very small scale. We're trying to scale it up to these very large trials.
Yeah, and I can't remember if we answered this or not, or we discussed it with obviously Yamanaka factors aren't going to
Yeah.
work because there's no epigenome in the way that the
Right.
nuclear DNA has an epigenome. Is there an analogous process for
Yeah.
rewinding, or we just get the stem cells which are already rewound, the mitochondria are already young? Is there a way to take old mitochondria and rewind them without going to stem cells, or do induced pluripotential mitochondria, like stem cells?
No, no, that is a very, very good question. So there are people who are trying to fix the mitochondria in the body without going to an external bioreactor. There's really two camps. Okay. There's two approaches. There's those of us who say, oh, we're going to do this in a bioreactor. And then there's those who say, oh, no, no, we're going to figure out how to do it in the body. And of course, I'm a bioreactor person. I don't think that the in-body solution is going to work. And I'll tell you why. The people who are going to be doing this are going to be 80, 90 years old. That's really who we're talking about. Because younger people, they're probably not going to do something this powerful. Okay. So this is a very big treatment. So the elderly people who are 80, 90 years old are chronically energy depleted at a cellular level. I mean, their bodies are barely hanging on as it is. If you try to go in there and repair those mitochondria, I say it's like trying to fix the engine of your car when you're driving down the freeway at 60 miles an hour. You know, I just don't think it's a good idea. I think it's risky. A lot of the changes that we're making in the mitochondria, the body already can do it, but it just can't. Your body just doesn't have enough time and space and energy left to keep the mitochondria young. If it could have been doing this when you were 90, then we'd already be living to 200. If it already done it, we have to get outside our bodies. We're a closed system. We're pretty much optimized. We're going to go outside of that closed system and use a bioreactor where we have infinite space. I mean, when I say a bioreactor, it might be as big as a room for all I know for one person. We have a lot of space. We can use an infinite amount of energy. We can do have all kinds of scientists watching it and quality control. And you don't inject those back into your body until you're really comfortable that they're really healthy. Okay. I just think that that's a more practical way to do it.
Yeah. Well,
Yeah.
looking forward to the future, if you could wave a magic wand, let's say 10 years well, no, let's say 5 years. Let's push it. Let's say we're aggressive, and between 5 and 10 years, if this were more widely available, what would the use case or the scenario be for, XYZ? You and I are 90. We're ready for our stem cells. What would we experience? Not our stem cell, our mitochondrial transplant.
Mitochondria.
What would we experience?
What we'd experience is we'd go in and it'd almost be like getting chemotherapy, except the reverse. You go in and you get this long infusion of mitochondria, and it's really just like getting a blood transplant. Okay. There's a bag of mitochondria and they drip it into you. And at the end of it, you feel like $1,000,000, okay? Because all the mitochondria are just sizzling and they're going into your cells, and your cells are all, oh, I've got all this extra energy. The biggest danger actually is that you'll be too energetic and you'll go out and overdo it. So we're going to have to counsel people to do physical therapy and to do slowly, okay? So I think you could do, maybe let's say you do that over a year, maybe you get one of these a month. And by the end of that year, I'm hoping, I mean, nobody knows. I hate to make predictions, but my hope is that you're more or less 20 years younger, okay? Does that mean you live longer? Nobody knows, but you certainly will be healthier. You'll be 90 years old. You won't be losing your ability to walk. I mean, I have a 96-year-old mother, and she's losing her memory and she's losing her ability to walk. And I'd like to prevent that. I'd like her to be able to take care of herself longer, right? And I have some of my volunteers in our volunteer group that are 80-year-old tennis pros, and they want the mitochondria so they can play better. you know that's what I think will happen in their first 5-10 years. It'll probably be very expensive at the beginning, but that's just true of everything. I mean, like computers were very expensive in the early years, and then they got cheaper because we learned how to mass produce. The eventual goal that we have is we'd like to have factories all over the world just pumping mitochondria out by the ton. And anybody who hits the age of 50 can just go in and get some, and it's just an automatic thing. And that would reduce all these diseases so much. I mean, just Alzheimer's. If you could just cut Alzheimer's by 50%, that would save unbelievable amounts of money and heartache for the world. So it's kind of this mission, to try to improve the health of the world. So
yeah, this has been such a great conversation. Tom, is there anything we didn't cover that you wanted to mention or that we need to touch on?
I just want to say, people often say, well, okay, so when are you going to start human trials? I'm going to say it again. We're doing it. I mean, they're doing trials in kids. I've got 20 some odd elderly volunteers, some of whom are, I've got scientists and physicists and doctors and VCs and Silicon Valley CEOs and I've got all these volunteers who are saying, yeah, I'll do it. Everybody's like, I'll be the guinea pig. So we're looking for people to help us do this. So, that's what I would say is we're looking to build our network. So
yeah, well, this has been such a great conversation, and we're definitely going to do this again. I want to have you back again and get some deeper and get the progress on this. But for today, I think, how can people follow you on social media and the website for the company? Could you?
Yeah, the website is mitrix.bio. And if you look up Mitrix Bio or Mitrix Mitochondria on Google, you'll find us. We're all over the place. And then I post a lot of stuff on LinkedIn. And so if you find us on LinkedIn, we have a lot of updates. So we try to spend a lot of time educating people because we're trying to spread the word. So
yeah, and it'll be in the show notes as well. And it's Mitrix, not Matrix. It's Mitrix
That's right.
with an I. If you're listening to this,
yes, Mitrix. Sometimes people call it Matrix. That's fine too. So,
well, thanks again, Tom, for this. Is such exciting work, and thanks for spending an hour with us. We really appreciate it. This has been great.
My pleasure. Well, thank you for letting me talk. I appreciate it.
If you are enjoying this program, please hit that subscribe button, or even better, leave a review. Your support makes it possible for us to create the quality programming that we're continually striving for.
Can I start? Is it recording?
It's already recording.
Oh, sorry. Okay. This is for general information and educational purposes only, and it's not intended to constitute or substitute for medical advice or counseling, the practice of medicine, or the provision of healthcare, or diagnosis, or treatment, or the creation of a physician-patient or clinical relationship. The use of this information is at their own user's risk. If you find this to be on the value, please hit that like button to subscribe to support the work that we do on this channel. And we take your suggestions and advice very seriously, so please let us know what you'd like to see on this channel. Thanks for watching, and we hope to see you next time. You should say that.
That's good. That's great. That's very good. You like it? You want to do it one more time, or is that good? I think that was good.
Yes. You need to save the recording.
All right.